When you wish upon a star. Actually, you're probably a few million years late. The star might be dead. Gosh, what does that mean about your dreams? About your wishes? In this lesson of NG Chem, we're going to be talking about the universe. This lesson is a lot about the scale of the universe. So we're going to start off small and build up to larger and larger and larger, the universe. So with small stuff, we're going to talk about asteroids first, so things that might be measured in meters. I've got an excellent video here that I got off YouTube. It's a company called Metal Ball Studios. That's the YouTube channel. And if you type in asteroid size comparison, you can watch this video right from them. And I've got the link listed right here, so if you'd like to watch this video without me talking over it. But I love this video. I love this company because they put things to scale, and this is an asteroids to scale, but they do it with all kinds of other things. So let's get going and take a look at to scale some of these asteroids. Let's take off the sound. We don't need the sound here. I'll talk over you here. So the first example here is an asteroid. It's 4.1 meters to 2008 TC3. This asteroid actually went into Earth's atmosphere back in 2008. That's what those numbers indicate here. And so that's 4.1 meters. And as we go up, we see these size comparisons to what it would look like to a house truck. Here's an asteroid bigger than the Eiffel Tower, which is insane. And we're going up, and now the diameter of these are getting over a kilometer in diameter. Huge. It was 66 million years ago when the dinosaurs went extinct. An asteroid hit Earth, and it's believed to have what caused the mass extinction of the dinosaurs. It hit in Mexico. It's an asteroid called Chicxulub. I think I'm saying that right. Chicxulub. And that asteroid, if you take a look at the size of these things here, was estimated to be between about 11 kilometers in diameter, so it could be smaller than Eros, up to about 80 kilometers in diameter. So these next few that we're going to see here are about the size of the asteroid that hit Earth 66 million years ago that caused the dinosaurs to go extinct. So maybe a little bit smaller than this one, but something in this range here caused a mass extinction of about 75% of life and species on Earth. Crazy. So that's here, but as we take a look at the scale, we are getting larger and larger and larger. Now, something I'd like you to pay attention to, as they get larger, there's a larger gravitational field on these objects, and as we start to get larger, we start to see the asteroids become more spherical. More gravity, things become more spherical, because if you put pressure around something, a sphere is the smallest volume it could make. And here we finally end with Cirrus. And Cirrus is in the asteroid belt, but this is actually the closest dwarf planet to Earth. But it's considered a dwarf planet, not a planet, because it's in the asteroid belt. To be considered a planet, you need three things. It has to meet three criteria. One, it has to be large enough to be spherical. And you can see that Cirrus is large enough to be spherical, where something like these guys down here orbiting the sun wouldn't be considered a planet. Which leads us to the second one. It has to be orbiting the sun. So it has to be spherical and it has to be orbiting the sun. And Cirrus does do both of those. It is spherical, it does orbit the sun. But the third rule is it has to have what they say cleared the neighborhood. It has, because what's happening is that if it's orbiting the sun in a pattern where other things are orbiting in that same neighborhood, that same area, eventually gravity will attract those things together, and that will finally form the final product, the final planet. So Cirrus is not considered a planet. It's called a dwarf planet because it hasn't cleared the neighborhood. In its pattern, we have the asteroid belt. That the asteroid Chicxulub was around this area here. That's how big it was. It was these guys in this area here, a little smaller than this one at the max, but you can barely see it here. Something like this hitting Earth on the other side of Earth is causing mass extinction. So they're not necessarily that big. Now, the good news is these larger objects we can see and we can predict their orbit. And it doesn't look like anything this big that's orbiting around. We can predict it. Within the next 100 years, it's not going to impact Earth or anything like that. After 100 years, it's kind of hard to predict asteroids because asteroids are not just being affected by the gravity of the sun, but they're also being affected by the gravity of the planet. So after 100 years, the prediction's kind of hard. But in our lifetimes, getting hit by something huge like this, very, 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 actually it's not even unlikely. What they say, it's not going to happen. The little teeny small ones that we can't see, that's another story. Now we're going to talk about the diameter of some celestial objects in our solar system. So first we're going to talk about our moon. The moon that orbits around Earth is 3,474 kilometers in diameter. The closest planet to the sun is Mercury, measuring 4,888 kilometers, which is it's about 1,000 kilometers in diameter more than the moon. So this is not a very big planet. Mercury has a very, very thin crust, and it seems to be extremely dense for its size, and it's indicated that it's pretty much all iron. It's an iron planet. When planets are forming, they're forming from the materials that eventually make up a sun. If you remember, we talked about stars and protostars, and that's random materials are out there. And how could you get just random materials make an iron planet when everything is kind of being spread out? The theory is that Mercury was once a planet something like Earth, where Earth has an iron core, and it got hit by something large, maybe one of those large asteroids at the end of the video we just saw, and it shattered and destroyed that planet. And Mercury itself is actually the core of what once was a planet, and that's a really interesting theory. Anyways, Venus is 12,100 kilometers, and Venus in size, gravitational-wise size, would be the most similar planet to Earth because Earth is 12,700 kilometers in diameter. So Earth and Venus, very, very similar in size, and these planets are done, to the best of my knowledge, to scale. They look very scaled properly on how they would look next to each other. Mars is about half the size of Earth. Earth is 12,700 kilometers. Mars is 6,780 kilometers, so it's much smaller than Earth. So I mean, we'd be much lighter on Mars. Then we have our massive Jupiter. Jupiter is the largest planet in our solar system, and it's got a diameter of 139,800 kilometers. The next largest is Saturn, 116,000 kilometers, and it's believed that the moon, the rings around Saturn were once moons, or a moon, or two moons, and they crashed into each other, and this is the debris that got caught in the orbit around Saturn. And given enough time, this debris could form another moon if the moons outside, there's a lot of moons around Saturn, if the gravitational fields of those moons are not preventing it from coming together. So their gravity trying to pull towards each other. If there's other moons interfering with that, it might keep the rings. But I've heard different stories about that. Uranus is 50,800 kilometers, which is very, very similar in size to Neptune, which is 49,200 kilometers. So these are both about 50,000 kilometers in diameter. But let's not forget, what's powering life on Earth for the most part is the sun. About 97% of our energy comes from the sun. 3% of our energy comes from our geothermal, comes from the hot vents that come out from Earth's core. Anyways, 1,388,000 kilometers in diameter is our sun. So these distances are not to scale, but the objects are to scale. So let's talk about the distances, okay? So if the sun is over 1,000,000 kilometers in diameter, and Earth's just 12,700, the distance between Earth and the sun is roughly 150 million kilometers. So 150 million, but in this picture here, the sun is roughly 1 million. So this distance is not to scale. It would be very, very, very far apart. But when we put the planets and stars and stuff like that together, it's impossible to put them together and still be able to see things. So let's take a look at how far away Earth should be. If you take the distance Earth is from the sun and divide it by the actual size of the sun, you could fit 107 suns between Earth and the sun. So if you put out 107 of these, which I did, it would go off the screen, you go onto another screen, go off the screen again, go onto another screen, and almost complete that screen before you would place Earth. So if the sun was here, we would have to go off the screen several times, 2 times, and on the third screen is where we put Earth. But now Earth is not to scale, because if we take a look, remember before the sun was huge and Earth was just a little dot. So if the sun was this size, we wouldn't even be able to see Earth. So this little teeny speck that we wouldn't even be able to see would still be an enormous distance away from our sun. A lot of pictures and stuff like that, you kind of get the image like, you know, here's the sun and Earth's orbiting it like this, but the distances are just enormous. So anyways, these are big numbers. We're talking 149,597,871 kilometers. These are big numbers. So what we're doing now is we're starting to move to a different type of unit. And that new unit we're going to be talking about is an astronomical unit. 1 astronomical unit is roughly 150 million kilometers. 1 astronomical unit is the distance from the sun to Earth. So the sun to Earth is an astronomical unit. So when we talk about astronomical units, if you think about this distance here, and we say 2 of them, then it would be twice the distance. So let's look at the distance of our planets in astronomical units. So Mercury is 0.4 astronomical units away from the sun, which is 40% of the way to Earth. So if you're traveling from the sun to Earth, when you get to Mercury, you're at your 40% mark. Venus is 0.7 astronomical units away from the sun, and of course Earth would need to be 1 astronomical unit from the sun, because Earth and the sun is how the scale was made. Once we get past Earth, we go to Mars, which is 1.5 astronomical units, so that means it's halfway between Earth and the sun is where you'd find Mars. So these lines are not to scale at all, are they? Because if Earth and the sun was this distance, about the halfway point would be Mars, so it'd be a little bit further out. After Mars, we have the asteroid belt before we get to Jupiter, and it's believed, from what I understand, the asteroid belt did not form a planet because Jupiter is so massive. The gravity, it's orbiting the sun because of the gravity of the sun, but the gravity pull towards itself to make a planet was interfered with because Jupiter's mass coming around there, it kind of messes this up. So the asteroid belt stays asteroids and not a planet. Anyways, the asteroid belt itself is a whole astronomical unit thick. So the distance from Earth to the sun, those 107 suns that we talked about before, that's how thick the asteroid belt is. It starts at 1.2 AU away from the sun and ends at 3.2 astronomical units away from the sun. We get to Jupiter, which is 5.2 astronomical units away from the sun. Saturn is about double the distance from Jupiter. So the distance from Jupiter to the sun would be this distance here. You would have to cover it again because that's roughly 5 astronomical units. You're going to 10. So that distance again would be where Saturn is. So remember, these distances are definitely not scaled properly. So we're at 10 now. To get in, just like Jupiter to Saturn, we doubled the distance, so 5 to 10. If you could get to Saturn, you have to go that distance again to get to Uranus, because you go from 10 astronomical units, 10.1, all the way up to 19.2, so about 20. So you go, it takes about 10 to get to here, and it takes 20 to get to here. So whatever distance you traveled here, you have to double that to get to Uranus, and then you have to add another 10 to get to Neptune. So the distances here are very, very far apart from each other. 30.1 for Neptune. After Neptune, we have the Kuiper Belt. The Kuiper Belt has a collection of asteroids and material in there, and also 3 known dwarf planets, including good old Pluto. When I was younger, when I was in school, when I was your age, as a younger person, I remember Pluto was a planet. We had 9 planets, not 8 planets, and Pluto was the last planet. But since then, with more sophisticated telescopes, we have found that Pluto is not alone. There's a whole lot out here with different dwarf planets, and it's orbiting together in this area that's now called the Kuiper Belt. And because Pluto is spherical and it does orbit the sun, it was called a planet, but we then learned that it hasn't cleared the neighborhood, all these other things here. So that's why Pluto's no longer part of the planet club. Sorry, buddy. Okay, so Proxima Centauri is the closest star to our sun. It's actually part of a triplet group. This star's not alone. It orbits 3 other stars orbit together, and this triplet group is something you might have heard before. It's called Alpha Centauri. Alpha Centauri is the closest group of stars, but it's kind of like in the sky it looks like one. But Proxima Centauri would be the closest star to us, and it would be 268,770 astronomical units away. So now the astronomical units, they're getting so large that we have to move to another way of measuring distance. And that way is going to have to do with light. Light travels. Yes, light does travel. When you turn on the light and it comes in your room, it's actually traveling from the light to you. It seems instant, but actually it is traveling. It's taking time to get to you. It's going really fast. If you stack up a meter stick, and stack 300 million of them, that would be long, 300 million meter sticks in a row, that's how fast light travels in 1 second. So it's moving extremely fast. It seems instantaneous to us, but when we get in huge distances in the universe, this speed is important. So if it's traveling 300 million meters per second, that would mean in 1 year, light will travel 9.5 trillion kilometers. So it does travel a distance, and so 9.5 trillion kilometers in 1 year, or since we were talking about astronomical units, 1 light year would be equal to 63,000 astronomical units. So now let's go back to Proxima Centauri. In light years, and that's the way we would talk about distances this far now. Once we leave our solar system, we start talking about light years. The very closest star is 4.27 light years away. That's extremely far away. That's the closest star. When you look up at the sky, that's the closest star to you. Some other forms of measurements here. The Rosette Nebula is 5,000 light years away. And this nebula itself, to go from one end of the nebula to the other end of the nebula, is 130 light years in diameter. That's crazy. Think about, to just get to the closest star from Earth is 4 light years away. This nebula, the size of this nebula itself is 130 light years in diameter. Things are getting enormous, guys. The Milky Way is the galaxy we reside in. And in the Milky Way, there are billions of stars making this beautiful spiral. We're in a spiral galaxy, and it's spinning around. In this picture, it's spinning around in a clockwise manner, as we kind of see. You can kind of see that twisting there, that clockwise twisting. And to get from one edge of the Milky Way to the other edge of the Milky Way, it would be 170,000 to 200,000 light years in diameter. So it's huge. And our star is just one of billions of the Milky Way, and our planet is just one of many, many planets. But planets orbiting different stars, not our star. Our planets are called planets. We call planets around other stars exoplanets. EXO planets. Exoplanets are planets that go around other stars. So in our Milky Way, there are billions of stars and billions of exoplanets out there. So we're starting to feel kind of small here. Another type of galaxy is an elliptical galaxy. The Maser 59 galaxy is about 50 million light years away, or 50,100,000 light years away, so 50.1. And when we get to this point here, if you remember the metric system, when you start to move the decimal point over to make it a more manageable number. When we move it over 1,000 times, that's a kilo, and if we over to the millions place, this M doesn't stand for million, it stands for mega. So after kilo comes mega. So this is 50.1 mega light years away. And this is an elliptical shape. And this is not just one star in a glow. This is a galaxy. So these are millions of stars that's so far away. It makes this glow kind of a look, but they're all individual stars and they all potentially could have their own individual exoplanets. The last type of galaxy shape we're going to talk about is irregular. Irregular is basically anything that's not spiral or elliptical. They could be anything else that's irregular. So here's an irregular galaxy, and it's got a, I don't know the story behind the name of this one, but it's NGC 1427 Alpha Galaxy. But sounds like an address. Anyways, it's 52 mega light years away, 52 million light years away to get to this galaxy here. And that, again, just the odd shape, it's irregular. It's called irregular. It's not elliptical, it's not spiral, it's irregular. Okay, so we're not the only galaxy out there, guys. There's lots of galaxies out there, and the galaxies closest to us seem to be associating with each other. These galaxies that are in proximity to us are called the local group. A group of galaxies, a collection of galaxies is called a group. Our group is called the local group. And in the local group, there are at least 80 different galaxies associated with each other. The Milky Way, ours, is one of them. The largest galaxy is Andromeda, which actually is also the closest neighboring galaxy to us. So Andromeda is the closest to us, and it's the largest in the local group. The Milky Way is the second largest in the local group, but we have at least 80 other galaxies in this group. The local group is 9.8 mega light years in diameter. So 9.8 mega light years to get from one end of the local group to the other end of the local group. But, so our galaxy is associated with other galaxies, which is called a group, and our group is associated with other groups, and this is called a cluster. Our group is called the local group, and our cluster is called the Virgo supercluster. The cluster, remember, clusters have are made up of groups, and groups are made up of galaxies, and galaxies are made up of solar systems. So the Virgo supercluster contains at least 100 galaxy groups and clusters, including the local group. So we are part of this here, and here would be our local group, which would have 80 galaxies, including the Milky Way in here, and it's part of a collection of other groups as well, and they are associated with each other. They're kind of grouped together, and then that would be in diameter 110 mega light years in diameter to transverse our Virgo supercluster. That's our cluster, and there are more clusters, not just ours. This happens to be the one we're a part of. Oh my gosh, we're so small. Now, the most distant galaxy that we've been able to see is NGZ11 galaxy, or I'm sorry, GN, not NG. GNZ11 galaxy is the furthest galaxy that we're able to see as of the time I'm making this video and the research I did, and that would be 32 billion light years away, or 32 gigalight years. When we get into the after it goes kilo, thousand, mega, million, and when we get to billion, we are at giga. And if you guys know anything about your computers, your hard drives right now are measured in terabytes. So trillions would be tera. So anyways, billions, giga. So 32 gigalight years would be how far away the most distant galaxy that we can observe. The observable universe. The observable universe would be 90 gigalight years in diameter. So 90 gigalight years in diameter, roughly. So we can see, observing from where our point is, would be the center of what we can observe. We can see in different directions as far as about 46 gigalight years in different directions. This is what we are able to observe. Beyond 46 gigalight years, 46 billion light years, we just don't see anything anymore. So the interesting thing about measuring things in light years is a year is time, and it's also a light year is distance. So when we look at Proxima Centauri or the Alpha Centauri triplets, we're seeing something that's 4.27 light years away. So the image we see from faraway objects are older the further away they are. In other words, what we're looking at, that light that traveled from this star to Earth when we're looking at it, it's been traveling for 4.27 years at the speed of light. So what you're actually looking at when you look at the star is something 4.27 years ago. If it's changed, if it blew up, if it's not there anymore, when we watch that happen, we're going to be watching it happen 4.27 years after it happened. And if there was life and they were watching us, they're watching us 4.27 years in the past. So if Alpha Centauri was looking at us right now, they're looking at Earth 4.2. The time it took the light from Earth to get to them was 4.27 years. So the further away you go, the older it is. So the Icarus star is 14.4 gigalight years, so 14.4 billion light years away, the Icarus star. So that means the light we're looking here is 14.4 billion years old. Odds are, Icarus star today at that location, wherever it is, doesn't exist anymore. It's probably a dead star. But for us, we keep seeing the image because that image took 14.4 gigalight years to get to us. The universe is 13.77 billion years old, with a give or take 40 million year factor. So 13.77 billion years old plus or minus 40 million years. So having said that, if the universe is 13.77 billion years old, you would think all you can see is things that are 13.77 billion light years away, because that's how old it is. Older things, the light hasn't got to us yet. And that is true. If that's true, though, how can we see Icarus? Icarus is 14.4 billion light years away. How can we see it if it's further than the age of the universe? This is how. Icarus has a red shift to it. Icarus is moving away, the Doppler effect. As it moves away, it stretches the wavelengths out, and we can calculate by how far those wavelengths are stretched out, how fast it's moving away. So technically, when we look at Icarus, we're looking at light that was emitted to Earth 9.34 billion years ago. 9.34 billion years ago, that light came to us. And because we can see how it's moving, we can then say where it is, because we know the speed that it's moving. We can then see and figure out that it is actually 14.4 gigalight years away. The image we see versus where we know it is different. So we calculate to where it is. So we're actually, even though the universe is 13.77 billion years old, if nothing was moving, that's as far as we could see. And as time goes, we'll start to see further and further and further, because light that's coming towards us will finally get to us. However, the universe is moving. Things are moving. They're moving away from us. And we're going to talk a lot about that more in the next test. Everything's moving away. And so because things are moving away, as it's moving away, it's sending that light to us. And when that light finally gets to us, we are able to calculate the speed that it's moving and the direction. And so what we can observe is actually greater than 13.77 billion. Again, so the further away it is, the older image that we see. So having said that, the older the stars are, like Icarus, it's very far away, and we're looking at a very old star. The image took a long time to get to us. We're looking far into the past. So older stars like Icarus are composed mostly of hydrogen. We can look at the spectrum of light and break down the spectrometry, and we can see what elements are in there. So the older stars we see are composed of hydrogen. We call these metal poor. These stars are metal poor. Younger stars like our sun have spectrum of metals in it, and our solar system has metals in it. I mean, I'm wearing a gold ring. This was forged from a star, supernova, by the way. That's how gold gets made. So the younger stars have metals in them, and the planets around them, or in the case of not our sun, exoplanets, they can have metals in them. They are younger because what happens is the old stars these are main sequence stars. The old stars form the hydrogen, they form the helium, and then the hydrogen fuses to create the helium. So in main sequence stars, they're mostly made up of hydrogen. And once the hydrogen gets converted to helium, the star death starts to happen. So most of the life is hydrogen. And then as it converts to helium, then the star expands and it starts getting, the core gets very dense. The helium, this is again review from the stars unit that we did. So the helium then starts fusing because it collapses in, it gets more dense, and the helium starts forming elements as large as iron. Eventually, that runs out. There's no more fuel for the fusion, and everything crashes in on itself, and boom, a huge explosion, and that's a supernova. So the supernova, this is the process that makes all the other elements that are larger than iron, things like gold, like I mentioned before. And then it all flies out and makes a cloud, and those clouds are called nebulas. And then that nebulas can mix with other things or themselves, and eventually gravity will pull the nebulas back in, and it'll start forming a disk, and it'll start spinning, and that will make a young protostar, and that will make protoplanets, and then you get a new star. And in that new star, you might have some metals in it. And like our sun has metals in it, and that would be why. So we have a younger star, but we can actually look back in time and see the older stars that don't have that. And we kind of get the idea of this history of chemistry. I hope you guys enjoyed that. Good luck on your quiz. Let me know if you have any questions.